Hi, good morning, everyone. How are you? Many thanks for your time and for joining. So this is SRv6. I would like to give you an update on the technology and the deployment status. Here. So first is really to start with a double thank you. So it's really a thank you to the lead operators, thank you to the ecosystem partners, to the academic partners, IETF, and the Cisco segment routing team, because this year is actually the 10th anniversary of the segment routing project. Segment routing started when a Cisco colleague, he was driving actually from Rome to Brussels. And along the journey, there is one tunnel, that is the tunnel of Gotardo, that is often congested. And so the question is, well, what do I do if this tunnel is congested? So what do I do if this tunnel is congested? And this started the realization that as human beings, when we need to reroute, we don't send a guy in a horse with a sign that has to identify me and my car and is telling me turn left or turn right. So that is SRv6. No, instead we take a way simpler approach that is just simply to say, well, go to the shortest path to Chamonix, take the Mont Blanc tunnel, and then take the shortest path to Rome. And so this kicked the idea that we can do way simpler things in networking, and we can really simplify and make something that is leaner and more scalable. So really, over these last 10 years, we have achieved fantastic things with segment routing. Today, I only have 30 minutes to give this presentation, and so as always, we maintain the segmentrouting.net website. As I only have 30 minutes, I will give you a bit the highlights. I will explain you what is the new things. However, all of the detailed information, because I won't have time to cover it, you have it here. So you have the pointers in the slides, the links. And so you will have very detailed trainings, demos, etc. So deployment status. SRv6 is really achieving record deployment status, the same as with SRMPLS. We only had 3 years of commercial deployment, so we started in 2019 with SoftBank. And already today we have over 100 million subscribers whose services are supported with SRv6. We have over 100 deployments, 14 of them with public reports across the web, service provider, and enterprise, and across different geographies, so in Asia, Europe, and America. Here you have the list of a few of the operators who have publicly announced their deployments. The new ones are in blue, and to highlight a bit that I will speak about later, Rakuten, Alibaba, and Bell Canada. So really, we are really happy to announce that in the past 3 months, Alibaba has deployed a full stack SRv6 network. From the application socket up to the peering link, full stack SRv6. It has been a great collaboration with the colleagues from Alibaba, with Joan Chow, Dennis, and Roy. And really here, one of the key things is that this deployment, it has not only been done just with Cisco ISXR routers, but also they have leveraged, for example, white box devices with Sonic. They have also leveraged the SRv6 support in Kubernetes. So really, beyond the use case, it has been a very, very interesting journey. We have a very strong commitment to lead operators to deliver standard-based technology, to have a vendor ecosystem, very rich vendor ecosystem, to also deliver a very rich open source ecosystem, and I think this is achieved. We already had 3 proposed standard RFC, so RFC 8402 on the segment routing architecture, RFC 8754 defining the SRv6 data plane, so the segment routing header, and RFC 8986, so the SRv6 network programming. Throughout the past few months, we have added 4 additional proposed standard RFCs covering the ISIS, BGP, OAM, and the segment routing policy. So really, this is a way faster speed of standardization than norm at IETF, and this is really a sign of the industry endorsement towards the SRv6 solution. We have a very rich ecosystem, not only from a vendor point of view, but also from an open source point of view. You have all of the details there. And we also had many successful interops, either at the NTC, at the Japan events like the ShowNet or the Net1, or NANOG. So the first technology that I would like to describe about is the stateless and scalable network partitioning for 5G slices. So the first process whenever this router R1 is receiving a packet is really to do a lookup on the destination address to determine which is the egress outgoing interface that is shown here in green. Now, if I want to partition my network, if I want to build partition for 5G slices, then what I will need to do is something very simple. With this technology, what we need to do is only to look into the partition ID, which is going to be a new field within the first 40 bytes of IPv6 header at a fixed offset. And I'm just going to select into which partition I need to schedule this packet. And then on top of that, obviously, I need to do a lookup on the DSCP to determine into which particular queue I'm going to put this packet into. So this is a very simple solution for doing the network partitioning. It is completely stateless. The destination address, the partition ID, and the DSCP, there are 3 fields that are within the first 40 bytes of the IPv6 header, so it's extremely easy for the hardware at a fixed offset. So there is no state, there is no classification, there is no DPI. It's just very simple for the hardware. This solution is also very scalable because actually these 3 fields, the destination address, the partition, and the DSCP, are actually orthogonal spaces. They are the routing, the partitioning, or the slicing, and the QoS. And this is a bit to compare with other proposals that are around at the ITF, where they are merging a bit the routing with the partitioning, and so it does not scale. So very simple solution. You have actually the demo link there. You can watch it, and quite straightforward. So then the core of my presentation, it will be around microseeds. So microseeds from an industry point of view, sometimes we call it SRv6 microseed, we call it SRv6 USEED, or USEED microseed, and at the ITF it is being standardized as the next CSEED. So, well, for microseed, we are really, really happy to announce that Rakuten has actually deployed SRv6 microseed in their network. You have all of the details there, but Rakuten has deployed SRv6 for their 5G end-to-end network slicing network. They have 2 slices in their network, one for low cost, another one for low delay. They are delivering the VPN services, L3 VPN and L2 VPN services with SRv6. And on top of that, they have all of their fast route, so 50 millisecond fast route technology with the LFA. In addition, with Rakuten, we have done a great innovation with this, for example, the BGP peak core and edge with SRv6 summarization, that is the UPA. And we've also done a lot of innovation for the segment routing bandwidth counters for the capacity planning. A second deployment, which has been very interesting, is Bell Canada. So Bell Canada is really interesting because they were one of the first operators that deployed SRMPLS 5 years ago. And they have very quickly transitioned from SRMPLS to SRv6 microseed. The reason for them to do this transition is because with microseed, they were getting better routing scale for the summarization, and they were also getting better hardware scale from the hardware point of view. They also wanted to have an end-to-end unified IP data plane from the application socket up to the peering link. And on top of this, they deliver what they call service programming, which in the industry is commonly referred to as SRv chaining, which led to a fantastic cost in the reduction of significant reduction of the cost for Bell Canada services. And this has been done together with Noviflow, the SRv chaining appliances. So very interesting use case. At Cisco, we already have feature parity between SRv6 microseed and segment routing MPLS since June 2021. That is why you're already starting to see deployment reports on SRv6 microseed. So we already have the support for TLFA and the macro loop avoidance. We have support for the flex algo to do the slicing, the low cost and the low delay with the automated steering. We have the traffic engineering policy with either both topological or service seats. We have any sort of service, layer 3, layer 2, or internet transport, the VPN gateway. And last but not least, we also have the IP summarization, which is going to be great because it means that you no longer need to support BGP 3107 to carry your host routes. We have a very rich ecosystem. You have all of the list of logo there. We had an excellent collaboration in between all of the different partners, and not only from a vendor point of view, but also very importantly from the open source point of view, which is quite impressive. So what is microseed? Microseed is a bit the continuation of the segment routing journey. And what was segment routing when we started? Well, segment routing, it's about going back to the root, to go back to the root of IP, to go back to the root of SIS, to go back to the root of BGP, and try to remove things which are needed, like, for example, LDP and RSVPD, that we removed them, and it was great. And so now with SRv6 microseed, what we are doing is we are continuing on that journey. We are going one step further. And so with microseed, what we are going to do is simply going back to the purity of IP, and the purity of IP is classless routing based on a subnet. And from a data plane point of view, this is just the longest prefix match that all of you know. So what is the benefit of building a solution on top of the longest prefix match? Well, first, that this is going to be straightforward to implement, piece of cake. And you saw the ecosystem before. We don't get such an ecosystem just by adding new functionalities. No, we get that ecosystem by really going back into the router, looking at the components, looking at the building blocks, and try to do things efficiently. And so, for example, just by leveraging this longest prefix match, what we get is things such as, for example, that we are able to support different sizes of microseeds that can be combined together in the same seed list. Or, for example, we can process multiple microseeds all at once in one single LPM lookup. And so just to take 1 minute and to compare it with MPLS. In MPLS, all of the labels have the same size. There is no flexibility. And in MPLS, if you want to process 2 labels, you actually need to circulate a packet, and this sometimes has a performance impact. So this is not an issue in microseed because we have the longest prefix match. So to illustrate a bit the benefit, one very simple example. If I have a PE device. On this PE device, I might have L3 VPN services. And these L3 VPN services, we know that at most I will have a few thousands of perfs. So it seems quite efficient to allocate the seats, to allocate the services, using 16-bit IDs. On the other hand, if I have layer 2 VPN pseudo wires, for example, here I will have hundreds of thousands of different entries. And so 16-bit is not going to be enough. And for the L2 VPN services, it's more interesting to allocate them using 32-bit identifiers. So really, with the longest prefix match, what I'm getting is this flexibility to mix and match and being able to merge them. Now, SRv6 microseed, it was invented in 2016, like one of the first building blocks of SRv6. So it's actually fitting very well within the segment routing header, so the proposed standard RFC8754. And it completely applies to the SRv6 network programming, so RFC8986, because any microseed can be bound to any network programming instruction. Now, SRv6 microseed is offering the best SRv6 compression. So what you have on this graph on the x-axis is actually the number of transport segments, okay? So the number of seats that you will use for doing your traffic engineering policy. And on the y-axis, what you have is the encapsulation overhead, so the MTU overhead that you are putting into the packet. If I look, for example, at 10, so at 10 intermediate segments for traffic engineering, with SRv6, the overhead is 208 bytes. With SRv6 microseed, you are going down to 64 bytes. So really, it's 3 times less. So quite significant. And we are the best with the microseed compression, and this is a bit to compare it with other proposal that was being discussed at the IETF. And so what you are seeing here on this graph, it's again on the x-axis, the number of transport segments. And in green, what you see is the compression efficiency that you are getting with microseed. And in red, what you see is the compression efficiency that you have with the alternative, that is this gzip or replace. And basically, you can see that for all of the cases, microseed is way more efficient. So better hardware scale. As we went through these deployments with Rakuten and Bell Canada, we have been able to look at the hardware, and we have been able to validate the steering of a customer packet coming into the PEC link, and steering it into a network slice with a VPN and traffic engineering for as much as 26 microseeds. Okay, so 26 microseeds that we push on this traffic engineering policy. Now, this was done at line rate. This was done on the NCS 57000. So in other words, Mercant Silicon, Broadcom Jericho 2 with 400 gigaports. And so just to compare it a bit, the number with MPLS, you can see that actually we are getting twice the number of segments with SRv6 than with MPLS. So the point is really not to do the comparison with MPLS, but the point is really to say, well, we have this technology, SRv6 microseed, that is really scaling. So 26 microseed is great, and to see a bit how the operators are using it. And in this same spirit of trying to go lean and trying to go back to the purity, well, in MPLS, when you have entries to a remote ISIS node, you actually have 4 entries in the data plane, and you also have 4 counters in the data plane. And so if you go with an SRv6 microseed fabric, you are simply reducing the amount of resources that you are going to use in your hardware. Better routing scale. This is also a very interesting data point that we got from the deployment from Bell. So at Bell, they had issues with the number of unique nodes that they were able to support in their SRMPLS deployment. Now with SRv6 microseed, they are able to get up to 15 million unique nodes in their network. which is 20 times more than what it was supported with MPLS. And if we look at the number of unique services that are supported in the network, with SRv6 micro:s, they are able to do 512,000 services. In MPLS, if we assume 20% of the label space, to 100K. MPLS does not support IP summarization, which means not only that you will have a smaller scale, but also that you will have to deal with PGP 3107 complexity to be able to carry your host routes. And then last but not least, seamless deployment. And really, this is something that Dennis Kai from Alibaba described 2 years ago in an excellent manner in the podcast that you have there. But with SRv6 micro:s, one of the key benefits is that most of the use cases will only do IP and IP encapsulation. You will not need to have a segment routing header. Because simply just by having IP and IP encapsulation, you're able to fit 6 micro:s into the IPv6 destination address. So really, for most of the use cases, this will be more than enough. And if you go a bit further and you look at the hyperscaler use case where you have this SDN controller, the SDN controller is actually computing the path, and it's encoding it into one single IPv6 destination address, and it's passing this address to the application. And the application is not aware. The application is treating this as something opaque, but it's pushing it into the packet. So it's really easy to start a policy from the application itself. So again, from an SDN controller point of view, this is something that is super simple. Then path tracing. This is one new innovation that I would really like to have more time to talk about, but I don't have it, so I'm just going to try to give you a bit the overview of the problem that we are trying to solve. And a bit with segment routing, what we try to do is to go back to the purity. We try to ask, for example, naive questions. And so the question here that is very simple is, how come that if I have a packet from node A to M, we do not know, and I guess that many of you, or maybe all of you, you do not know how this packet has been exactly forwarded in between the routers A and M. Because in reality, we know that here we have 7 valid ECMP paths, and we know that very likely the packet has taken one of those 7 ECMP paths. But we do not know exactly which one of the packets has been taken. And to go one step further, in some of the cases, there are things like, for example, AFib corruption. And it might be the case that some of the router, for example, the router B here, forwarded the packet into a completely different path that is not one of these green paths, like the path shown here in red. How do you know that this has happened? How do you detect this? How do you know how this packet has been forwarded? So what path tracing is trying to solve is this. It's going to give you, in a deterministic manner, it's going to tell you how the packet has been forwarded in your network. And on top of that, it's going to give you the timestamp at each one of the hops, and it's going to give you the load for that interface at each one of the hops. So to show in a very simple manner how does it work, let's say we're going to use this very simple example. And I'm going to create a probe packet that is going to go from the router A to the router M. In this probe packet, what I will have is an IPv6 header, like in any SRv6 use case. So source address A, destination address M. And following that IPv6 header, what I will have is an IPv6 hop-by-hop header, which is an extension header to IPv6. On this hop-by-hop header, I will have the path tracing option, which somehow you can see it as a metadata scratchpad. Okay, so it's going to be a space where each one of the routers is going to write what we call midpoint compressed data. This midpoint compressed data is going to be 3 bytes of information where we are encoding the outgoing interface ID, the outgoing timestamp, and the load. So somehow you can see this, maybe like a passport is the analogy that we use sometimes, because as the packet is traversing each one of these routers, the routers are going to stamp into this passport this information. So the router A here is generating this probe packet, is going to send it out, and just before putting it on the outgoing interface, the first thing that it's going to do is going to write into this path tracing option, is going to write, well, the packet is being forwarded on the interface from A to B. It's being forwarded at this particular time, and the load that I'm seeing on the router is X. Then the packet is sent out, the packet goes to the router B, and the router B I do all my lookups, I'm going to forward it, and just before I put it on the outgoing interface, I'm going to do the same. The first thing that I'm going to do is I'm going to write the outgoing interface, so this packet is being forwarded on the link from B to G at this particular time with this particular load. And the process goes on. And so the packet arrives to the router G, that I'm doing my lookup, etc. But just before forwarding the packet out, what I'm doing is I'm writing this packet is being forwarded from G to M, on the link from G to M, at this particular time with this particular load. So the basic intuition here is to give you full visibility into how this packet is being forwarded through the network. And then on top of this path visibility, we are also giving you the timestamp and the load so that you have a full characterization of the packet delivery path. This full characterization is written with a minimum overhead, so each one of these nodes is only going to write 3 bytes of information into the packet. And with this full characterization, basically you will be able to know how the packet has been routed and the state of each one of the routers in your network. And then what we are going to do is we are going to put this information into a time series database so that then you can go back and look up the state of your network for any point in time. So to make path tracing work, the key idea is that we need to monitor in the most basic pipeline of the router. Because any solution that would actually try to monitor like for example, punting to the CPU of the router and monitoring the CPU of the router, that is not useful at all. No, because we really need to monitor the same thing as your customer packets. And so we need to use the same forwarding tables as the forwarding tables of your customer packets. So really, the key idea is to engineer it from scratch so that it can be implemented at line rate, effective on any packet. That's why one of the key principles since we started has really been to extract the juice out of the router and try to get the most out of the router capabilities. And what this means is that we had to minimize the MPU parsing, we had to minimize the number of bytes that we return write, and not only the number of bytes, but also depth. Try to write at fixed positions so that we minimize the number of editing commands, try avoiding, for example, doing header insertion or resizing the header, and obviously minimize the MTU. So we have been working with different ASIC vendors and different ASIC architectures to get this implemented at line rate in many routers that you will see later. And so we are trying to minimize the hardware complexity by doing a very good engineering of the data plane, but we are also trying to minimize the hardware complexity by leveraging SDN analytics. So if we go back to the previous example, we had the probe packet in blue that was going from A to M. And here, when the packet gets to M, one very simple approach would be to say, OK, I'm going to process this packet on M, on the CPU of the router M. But that actually does not scale. The router M is not designed to do this processing and so on. So instead, what we are doing is taking a way more scalable approach, that is to forward all of these metadata to an SDN application. On this SDN application, what we are doing is, first, we are translating or we are processing this information. So for example, we are translating all of the midpoint compressed data into meaningful data. Okay, so we translate a list of compressed interface IDs into an actual path. We are deducing the timing and the load history and so on. But then also, because this SDN application has communication with the PCE, with the path compute engine, we can do quite interesting things. So for example, from the PCE, I can get the RIP information. I can get all the routing information. So I can get the RIP for each router. And from the path tracing, what I have is the information from the FIP, how the packets are being forwarded. And for example, this SDN application, what it can do is it can check whether there is any inconsistency in between the routing and the forwarding, which is quite interesting. So really, path tracing, it's something that at Cisco we are going to ship it in this calendar year. We had a very rich, very interesting conversations with Broadcom and Marvell at the very beginning of the project to design the data plane. This is already supported in Broadcom Jericho 2 SDK native. At Cisco, we have this running on the Cisco 8000 with Silicon One. We will have it shipping on the NCS 57000 with Jericho 2 Cisco SR9K. We have a very rich open source applications with Linux, FDIO, BBP. We also have an open source P4 implementation. And obviously, we are standardizing this at the ITF. So to conclude, simplicity always prevails. That is the key thing that we are doing with the segment routing project, is to try to go back to the building blocks, try to bring back this simplicity. Along the journey, we already removed LDP and RSVPT. We managed to very successfully reuse the MPLS hardware for SRMPLS, and SRMPLS was great. We foresee a lot of deployments for SRMPLS, and there will be a lot of future for it. However, the simplification journey is continuing with SRv6 microSID. And that's a bit where we are going, and more when we can deliver this with more scale and with functionality. So that's all. Many thanks. And if there's any question.
Tom from Cloudflare. First of all, thanks for that presentation. With packet tracing, I'm a bit wondering, you were explicitly mentioning this is super helpful in ECMP environments. It looks like an active monitoring solution. So how do you actually get to a point where, for example, because 5-tuple in regular ECMP environments, how do you get to the point where you know specifically for customer flows, it's going through there? Do you generate a PT packet for every single customer flow that hits your network?
Okay, so path tracing, it's indeed, well, the first phase that we are doing for path tracing is really to do this active monitoring, so we are generating probes. The idea that we have is we are going to generate probes with, in SRv6, we have what we are using for the ECMP is the IPv6 source address, destination address, and the IPv6 flow label. So we are going to use many different flow label values so that we are able to monitor all of the different ECMP paths in the network. And so that is the step one. So to really being able to monitor whether the FIP is working correctly from an ECMP point of view, and that we are using all of the ECMP paths correctly, and that we have the correct load balancing. Then as a phase two, indeed, you could try to apply it more as a passive approach and try to measure particularly customer packets. But as a phase one, what we are going to do is this active monitoring and simply just monitor that all of the ECMP paths is been working correctly.
Two simple questions. The path trace, could that be used in switches as well? Now you mentioned it in routers.
It's a very interesting point. Initially, we were thinking of routers only, but indeed, we will see. It's still very early. Like path tracing, we have only disclosed it to the IETF, and we started with it only maybe 1 year ago. But it's a very interesting piece of feedback, and we will see.
A second question. No matter if it's switches or routers, you might have some LACP tunnels with different routes. So it would be, I wonder if the path trace goes on the LACP interface or if it goes on the physical interface.
So it goes on the physical interface, and we consider that's enough for now. We will see in the future, but it's going on the physical interface right now.
Any other questions?
Yeah, Tom again. You had the P4 logo on your slide deck. Is there an open source GitHub repo that we can have a look at?
Yes. I don't know if it's here, the link, but anyway, on the segment routing website, there is a section on path tracing, and you have all of the open source implementations. You have a link to the P4, the Linux, and the BBP.
Any other questions? No? Thank you very much.
Thank you very much for your time. Have a good day.